Thanks, Abby, and thank you all for coming tonight. It's a pleasure and a privilege to be here and to be able to speak to you about some things that are really quite close to my heart. So, when people think about humans and their relationship to nature, they often think about something a bit like this. You've got ecosystems on the left there, and there's things that ecosystems do that really have very little to do with people. You know, a whale out in the open ocean feeding on krill quite happily. It's independent of people to a large extent, or so we hope. And on the other hand, there's things that people do, like making art, that are really done by people for people. And these things are kind of, they're neither good nor bad in their own right, but where I find the particularly interesting interface is in this middle bit here, where you have people and their interactions with ecosystems. So people use and rely on ecosystems for a huge number of things. People might be catching fish, but at the same time, they're impacting the ecosystem, and those fish have consequences for things out here in the other part of the human piece of the problem, basically. Now, I'm not entirely sure that I like this way of viewing the world. Right? It's one way that you can think about it, and obviously when I talk about a social-ecological system, this is the bit that I'm really focusing on here. So there are these things, but this is the part that's really relevant when you want to understand natural resource management. But there's a bit of an asymmetry here. So if we think about it, if we were to lose the human side of the equation, we might have ecosystems, and whales would still be happily feeding on krill, presumably in larger numbers than they do today. And we might just have a whole lot of happy little animals. And that would be how it is, right? But if we were to lose the ecosystem side of the equation, there would be no people at all. So I want to start off this discussion by saying people are hugely dependent on ecosystems in a huge variety of ways. And in our modern lives, we often forget that or ignore that, or it's easy to stop remembering it. But actually, this is where things stand. Without ecosystems, we are gone. All right, so where does this lead us on to? Scientists have been thinking for quite a while. This is some work that dates back to 2015, but there's been a recent update. Thinking about how many people can the planet support, and what kinds of resource demands do we place on it. So this figure over here identifies a set of what people have termed planetary boundaries. Again, it's got its issues, this particular way of viewing the world, but what you can see is that there's a whole set of things, for example, the amount of nutrients that we put into the Earth. The Earth is capable of supporting things within this zone here. This circle is intended to indicate that. And when you exceed that zone, things become a bit unstable or unsuitable for life. So, for example, the very high levels of nutrients that we pump into the environment through things like industrial effluent. And this in turn leads to, creates problems. For example, algal blooms. You might have massive algal blooms that stop you from swimming or drinking water. And that would be one consequence of that boundary being exceeded, going beyond what ecosystems can support. Now, if we think about these dynamics in a more dynamic way, these figures here on the right are intended to show you, so we have a stressor at the bottom here, something that's placing stress on ecosystems when it's in high quantities, from a low level to a high level. And on this axis, people have tried to put an ecosystem response. So that might be, let's say, the total number of species you have, or the abundance of species within an ecosystem. And what we see in many cases is that as the stressor increases, ecosystems have some capacity to deal with change. For example, forests grow and they absorb carbon dioxide from the atmosphere. And so ecosystems can regulate to some extent the burdens that people are placing on the atmosphere. But at some point, that ability to buffer or regulate what's going on is exceeded. And that's when we might see some kind of decline in ecosystem capacity. So the planetary boundaries offer a simple way of saying we have a safe operating space, which this boundary is intended to define. And when we exceed that, this is what we risk, this kind of decline or potential collapse. And this is the focus of what I'm speaking about tonight. So unless you've been living in a complete shell, and the fact that you've come out to this lecture tonight suggests you have not, you'll be aware that there's massive changes underway in the Earth's ecosystems. We're seeing habitat loss, climate change, pollution, overharvesting of many species. There's a lot of change in the Earth at the moment, and particularly in ecological systems. And it makes us feel like society doesn't care, but society cares. A lot of people care very deeply about these things. So how did it get this bad, and why aren't we fixing the problems? What's going on here? And it's not just about climate change. So when we think of the ocean specifically, there's many marine ecosystems that are being degraded or lost in some way. And I think there's at least broadly three possible outcomes. We might see some kind of recovery or adaptation of those marine systems. We might see things being simplified, so they'll still persist, but where you used to have, let's say, 50 species of fish, you're now down to 10. A simpler ecosystem that has the capacity to persist in the future, but without some of the biodiversity that we love and appreciate in our current time. Or it's possible that we might see collapse. And if we see collapse of entire ecosystems, there's obviously a severe existential threat to people. It's unclear, are we really at risk of collapse? So we've seen simplification in some places, we've seen adaptation in others. But what about collapse? We have to be aware of the possibility of collapse, I think, as a society. We have to contemplate this, even though it's not fun to think about what happens with collapse. Because if there's any chance of collapse, we need to confront it and do something about it. And it's unclear with the ocean how resilient is that system. How much can it cope with the stresses that we're putting on it? Are marine ecosystems going to collapse? And will we see the collapse of societies or industries that depend on the oceans? And how should we respond? So ecology doesn't really have the answers to this. Until recently, ecology had no formal definition of collapse. We've got a lot of quantitative tools for understanding ecosystem-wide impacts of things like rapid, patchy loss of species. But those tools are inadequate to try and add up to, are we likely to see collapse or not? And I would say that neither sociology nor economics really have the answers either. Because vulnerability research often focuses on what we call pulse perturbations, short, abrupt changes to which systems can fairly easily adjust and adapt. What's happening at the moment on the Earth is a much longer, slower perturbation, which we think of as a press perturbation. There's not a lot of press perturbations in human history, although there's plenty in the history of the Earth. There is archaeological research in the social sciences and quite a lot of work that's been done on why did ancient civilizations prosper or collapse. But often it's on very different systems from modern societies, much less connected, much less technologically sophisticated. In social-ecological systems research, which is an area that I consider one of my own specialties, there is a bit of a theory of collapse and reorganization, and I'll just talk you through this diagram briefly. So you can think of this, it actually comes out of ecology originally. If you think of a forest after a fire, you've got relatively little stock, so capital is low. As the forest grows, biomass increases, and you get to a point where you have a forest that's full of, let's say, mature trees and increasing amounts of leaf litter. That, at that point, makes that forest vulnerable to particular kinds of disturbance, particularly large fires. So a small forest, a young forest is less capable of supporting a big fire than an old mature forest. And at that point, if a fire enters the system, it can cause some kind of localized collapse of that ecosystem and a release of nutrients into the system. Out of that context, the legacies of that large forest and that fire grows something new. So there's a period of reorganization, and then that can re-enter some kind of growth curve. So you can think of this as a forest fire dynamic, but you also see it in many other spheres of life. So for example, if you think about a typical business or firm as it begins, take something like Apple Computers. They started off pretty small, they grew quite fast, they became very big. Then they had to do something different because their size made them vulnerable. They became inefficient, they became less able to keep up with modern technologies. And there was a reorganization. Maybe they fire the CEO or start adopting a different business model. That leads to some kind of adjustment in the business, reorganization, and then entering into a new cycle of growth. So it's a model that describes growth and collapse. But when we try to apply it scientifically, it's got a relatively weak empirical basis. It's poorly understood what drives these dynamics. It's very general. You can apply it to almost anything, which is always a bad sign for scientific theory. and it's got basically no predictive power. So it says that if you get too big and fat or too comfy, perhaps you're going to have some crisis coming up soon. And I have read comments that good business managers will actually deliberately precipitate crises in order to avoid getting to this point, right? So deliberately undertake some reorganization to prevent that kind of balkanization or becoming stale as an organization. Right, so we don't really have the science at this point to provide a rigorous science of collapse, and we need that kind of science because that's what's going to help us decide if we need to do something really different as a society. So what kind of science do we need? We need clarity on terminology and what is collapse. It often has lacked a clear definition. It's not the same as reorganization. So the figure I just showed you is talking about some kind of reorganization which many ecosystems go through naturally. Forest fires are not things that ecosystems are not adapted to deal with. So if there have been fires, probably before there were people, there were forest fires caused by lightning. And forests have grown and adapted to deal with that kind of perturbation. What we're seeing now is a whole set of perturbations that ecosystems are not adapted to deal with. So we need a definition that separates collapse from reorganization. We need to understand what the mechanisms of collapse are. What are the actual things that drive or cause collapse? We need examples, data, tests of mechanisms, and we need to understand how to respond. What can we actually do to prevent some of these things from happening in ways that impact human populations or quality of life? So there have been a number of efforts in the published literature to try and address this gap. Joseph Tainter is probably the most reputable of these different scholars, I would say. Tainter regarded collapse as a rapid loss of an established level of social, political, or economic complexity. So he framed it in terms of complexity. The trouble with this definition is that complexity is notoriously hard to measure. Unless you have a relatively simple system, there have been efforts to measure it based on information content, but that also is a difficult metric to try and measure or monitor. Jared Diamond, who's written a number of things about collapse, talks about collapse as a drastic decrease in human population numbers or in political, economic, or social complexity. So he built on Tainter's definition, but he added in this bit about the dramatic decrease in the human population. There's an economist, Roberts, who's spoken about economic collapse, and in economics this is regarded as a multi-year contraction of per capita income as a consequence of things like conflict, mismanagement, state failure, or international sanctions. So a different definition again. The Intergovernmental Panel on Climate Change, in one of their reports, acknowledges ecological collapse is not currently well defined or well understood. And Jared Diamond's work illustrates some of the problems of clarity. I'm going to take a brief diversion into this because I know some of you are interested in it. So Jared Diamond published this book, Collapse, which some of you may have read. It's a reasonably popular book for those who are interested in this kind of stuff. And it actually so outraged a group of leading anthropologists that they published an entire volume called Questioning Collapse, basically shooting down Diamond chapter by chapter and theory by theory. And if you're interested in this stuff, I'd recommend having a dig into this. Some of the chapters are quite academic, but it's also got some really interesting things in it, including chapters written by indigenous people who are descendants of some of the tribes that Diamond accuses of committing ecocide. So here's two examples of mechanisms that might explain collapse, and these come from Tainter and Diamond respectively. I'll come back to Diamond in a little more detail in a moment. So Joseph Tainter worked extensively on the Roman Empire, and he tracked, he used evidence from fairly well-kept records from the Roman administration, as well as a whole lot of stuff about the value of the denarius, the coins that the Romans used. So originally denarii were made of metal, quite precious metals, and over time the quality of the metal that the denarii were made from declined heavily, basically. And he uses this to track the decline, what he considers the decline of the Roman Empire. So it grew by conquest, but the cost of maintaining systems of communications, governance, and war also increased. Right? So until it got to a point where maintenance was too expensive, and there were no new areas to conquer that were worth the cost. So this figure below shows a kind of an economic depiction of this. This is the change in capital, and this is what happens over time. So with increasing bureaucracy, the cost of supporting that bureaucracy goes up and up and up. And at the same time, the benefit you get from that bureaucracy declines. So each new unit of bureaucracy you add brings less value relative to what previous units have. And at some point in Tater's thinking, that gap gets too big. The society can no longer support the bureaucracy it's created. And this might sound a bit like some of our universities to some of you. And that's the point where you see a decline or a collapse. I could say more about the lessons here, but I need to move on. Jared Diamond's focus is on overshoot, or ecocide, as he's called it more dramatically. An example here would be from Mayan society, which he considers to have reached ecological carrying capacity in a period when climate conditions were beneficial for farming. So they could produce a lot of food, support a lot of people. And then when a drier climate cycle hit, the population couldn't sustain itself anymore and led to famine, conflict, and a breakdown of social order, because in his view, they'd overused or overworked the environment. So Diamond's theory you can look at as human population size. In a good cycle, you get this blue line here. Carrying capacity goes up quite high. Then if you have a drop in carrying capacity, he's saying that's going to lead to potential collapse of some sort caused by famine or other things. Now, some of the issues with Diamond's narrative, overshoot doesn't really explain why populations don't just re-equilibrate. So this figure here shows you population size and time. And what we've done at these two red arrows is introduced a drastic decline in carrying capacity. The underlying model for this is a human demographic model, but it's also got a social network embedded within it where humans survive or die off. I don't want to get into the details of the model, but it's a reasonably sophisticated population model underlying it. And what you can see is actually that what you would expect if Diamond is correct, based on Diamond's hypothesis, is just some quite simple dynamics. The human population increases. It hits carrying capacity at whatever that is. It drops off when there's a reduction in carrying capacity, but it finds a new equilibrium. So there's no reason why this kind of shock, whoops. All right, so these are two examples of how collapse can happen. And then I was just explaining how, in Diamond's view, there's no obvious reason why populations shouldn't re-equilibrate based on his particular argument. So what it comes down to is that for collapse to occur, you need more than just what Diamond suggested. So a reduction in carrying capacity might possibly lead to collapse of a society if other sets of conditions are in play. And Diamond conveniently ignores a lot of those other possibilities. But in fact, they're 100% necessary for collapse to occur. Right? So you've got to have, for example, warfare or disease or other things that are actually the primary agent of collapse in that example. And two examples that you might find intriguing if you've dug into his work at all. You can still meet descendants of the original indigenous people who inhabited Rapa Nui or Easter Island. They still live there. And there was, in fact, if you look at some of the archaeological record, the main population declined. So although there was a big decline in palms, and there's been all this argument that they depended on the coconuts from the palms, and that led to the population collapse, as Diamond termed it. In fact, if you look at the timing of it, what really happened was there was an introduction of rats and a whole set of Western diseases when the Spanish first got to Rapa Nui. And that's really what's led to a big, I think the majority of the population decline. So Diamond kind of covers over these facts and obviously some of its more recent scholarship, but at the same time, I think the important take-home message there is that you can't expect any one mechanism to explain all collapses or to explain even necessarily one collapse. Collapse is almost always a conflagration, a combination of a whole set of different things that come together. So how can we define collapse a bit better? In this figure, we're looking at this is like a typical urban ecosystem. We might be looking at a quantity of something on that axis, something we're interested in. And the red line in each case indicates collapse. And we want to be able to distinguish a true collapse, which is the red line, from just the system varying a bit or bouncing around, a small shock, some adaptation, things going up and down in the way they do in normal cycles. From a shift like this, where you see a decline and then it recovers back up to some similar equilibrium, or from a gradual, slow decline, which is, again, not really what we mean when we say collapse. Collapse, this kind of shift, depending on the time frame, gives you time to adapt or respond or develop new technologies, whatever the case is. This is much less scary than the red line, which is a sudden and rapid decline in whatever quantity you're interested in. So to get this kind of clarity, we need to clarify boundaries. So what area are we talking about? How is it bounded in space and in time? What scale are we going to measure this at? What is the system? What are we actually looking at? You know, some things are integral to system identity and some things are not. So if you think about yourself as a person, for example, you probably look quite different now from what you did when you were 2 or 3 years old. But you're still the same person. You haven't collapsed just because you don't look like that anymore, right? There's things about you that are integral to that identity that people know and recognize about who you are, even though you've changed and grown through time. And it's the same with these kind of ways of thinking about social ecological systems. We need to recognize that some change and development through time is inevitable. But there's some kinds of change which would result in a loss of identity. So you might, for example, be able to lose an arm and you would still probably very much be you. But if you lost your head, that's a different story, right? So we need to distinguish between these different kinds of change if we're going to talk sensibly about collapse as an object of scientific study. So we can think of collapse using these 3 criteria. Firstly, you need to lose identity. So actors or system components, key interactions have to disappear for something to qualify as a collapse. Second, it needs to happen relatively fast so that it's distinguished from kind of gradual changes. For example, within a generation or 2 generations of a dominant system component, whether that's a tree or a long-lived organism, whatever it is. And then collapse has to also result in substantial losses of capital for it to qualify as collapse. So an average decline of some number, whatever that is, let's say 90% in the number of species, the area of habitat, total assets, human well-being, whatever it is. So this is what we're looking at when we talk about collapse, a very particular kind of quite severe change. All right, so these three conditions are essentially necessary for something to qualify as collapse. So we dug into this a bit more, looked at a whole range of different case studies, basically everything that I could find that dealt with collapse in a fairly clear way. So for this particular study, we looked at a range of kind of classical case studies, including a bunch that are discussed by Diamond, a set of ecological cases. There's lots of situations, for example, where marine fishes have collapsed, stocks have collapsed very soundly through overfishing. And also some cases where, for example, in Hawaii, we've had loss of basically extinction of endemic birds based on avian malaria. So these kind of things qualify as collapse. And then also a set of economic case studies and examples. So reaching across all of these different cases, we did a bunch of synthesis. I'm not going to go into details. But it turns out there's a whole lot of different mechanisms. There's at least 14 different mechanisms that might explain collapse. This is an example of one that you might not have thought of, or perhaps you have. So capture by elites. When the top of a hierarchy becomes parasitic on the bottom of a hierarchy, people in power become parasitic on those who lack power, leading to collapse once the support of the top of the hierarchy is sufficiently eroded. And you see something similar in fish populations, where in many situations adult fishes will feed on their own juveniles. And this is what this figure down here shows. So basically, normally you're sitting in an area where you have a stable equilibrium, and this is a stable point here. So I won't go into the maths in any detail, but basically the population should normally tend towards this value. But if you get a significant decrease in fish populations, that can be enough for that predation effect to push you down and basically drive the population out of business. So there's a whole lot of different ways that collapse can occur, and these connect to the way in which the system is structured. So I'll take a moment to explain this figure. On the vertical axis here is an axis of how networked you are. So this is peer-to-peer interaction. And what we've got here is a situation where things are quite highly networked. There's a lot of interaction between peers, and here, relatively low interaction. So this is at a single level of organization. How interactive are the elements, whether that's animals or people or locations? And on this axis, we've got a hierarchical axis, again going from low on the left over to high on the right. So how top-down is the system? The way the system is controlled, is it strongly hierarchical, or is it much less hierarchical? And if we cross these axes, we get these 4 different boxes. So The simplest one to think about is over here, where we've got relatively little interaction between peers and relatively little top-down control. So that's a kind of, in governance terms, that's anarchy. That's just every individual living their own life, individuals for themselves. As the level of networking increases, we might move up into this kind of situation. So you have a relatively flat situation socially, in which different nodes have a similar level of power or similar level of control over what happens in the system, and they're interacting. You could think of this as maybe like a small startup business. You know, when Apple computers started off in the garage, there were 5 or 6 of them, whatever it was, and they all interacted with each other in a fairly equitable way, right? At some point, as a society grows or as an organization grows, that becomes inefficient. It's not an efficient structure for getting things done because everybody's working in small clusters, and you have to struggle to get coordination across the different clusters. So then it tends towards one of these two models. So this one at the top here, which is both hierarchical and networked, would be termed polycentric. For many people, this is considered the ideal situation for governance, where you have multiple centers of power that balance each other out. Alternatively, you might have a more pyramidal system where you have, for example, a dictator at the top who tells his generals what happens, who instruct the people, and they deliberately try to break that trust that occurs or the other social links that occur at the lower levels of the hierarchy. So different, and this is relevant to ecosystems as well. So you have some organisms that live pretty much in an individualistic way. You have other things like food webs, which are very tightly structured, top down. Some situations where predation is a major driver of what happens in ecological systems. Other things where you have things that are more polycentric. So for example, in spiders, you might be getting predation between guilds. So a predatory spider eats another predatory spider. It's not nearly as clear-cut as a very top-down food web or food pyramid. And these different structures have different vulnerabilities. So a top-heavy structure might be vulnerable to something like elite capture, where the top of the pyramid takes too many resources from the bottom of the pyramid until the bottom of the pyramid can no longer support the top. Whereas a system like this is much less likely to experience elite capture, but it's got other kind of vulnerabilities that arise from the challenge of getting effective collective action organized in the right way. Right, so there's a strong relationship between the structure, the way in which interactions within a system are structured, and the likelihood of it collapsing by any one particular mechanism. So at this point, I'd like to emphasize 2 points. Firstly, collapse can happen in at least 14 different ways, and it's usually multi-causal. There's lots of different things that combine to cause collapse. And secondly, the kind of collapse that occurs relates to the structure of the system and to the key processes that are underway. Right, so far, quite theoretical. I've laid out some concepts and I've defined collapse. I've spoken a bit about some of the background thoughts that underlie some of these ideas. How does this all relate to us today? So historically, people have thought about human society and its growth as under a kind of a development model. So this is now really outdated, I would emphasize that. But back in the sort of 1940s and 1950s, this was the dominant paradigm. People thought that humans had evolved from relatively traditional societies with strong dependence on resources. Through a set of stages, they labeled this one takeoff in sort of true ambitious colonial fashion, a drive to maturity, and then high mass consumption. Right? So this is, as you might guess, coming out of an American setting where this was considered the ideal, where you can live in a wealthy society, where you can have high mass consumption. And population size is obviously a niggle in these kind of approaches to thinking what's ideal about the world, because high mass consumption is hugely wasteful, as I'm sure you all know. So what happens to population size? Well, this way of thinking assumed that there would be some kind of demographic transition to lower growth, to smaller, richer families. And you do definitely see some evidence for that. So in wealthy countries, family sizes tend to be quite a lot smaller than they do in less wealthy countries. Right? So there was enough empirical support for people to start taking this seriously. And in fact, this remains an underlying kind of subconscious policy driver for many wealthy nations in the world today. What people often ignore is that continued growth or development often depends on immigration from the periphery, from the less wealthy countries that are not at the center of the global economy. Or alternatively, a loss of surplus population from the core if the core is overproducing in terms of the number of people that it can cater for. All right, building on this, the economist Kuznets proposed that what happens as you get wealthier is that societies go through a gradual trend where to get rich they need to do a whole lot of pollution. This is based on the idea of the Industrial Revolution particularly. Societies pollute the environment to create technologies and other forms of wealth that then allow them to start to live a better quality of life. And then at that point, he argued, when they're wealthy, they then pay more attention to their surroundings and their environment. And that leads to an overall decline in pollution. So this is pollution on this axis, and that's per capita income on this axis. So he's basically arguing that as societies get richer, they have to go through a stage where they pollute a lot, mess up things a lot, and then as they get wealthier, they start paying better attention to their environment, because he regarded that as a bit of a luxury relative to the problem of just getting food and surviving. So these ideas have been, unfortunately, very highly influential, and there's a whole group of people that says, you know, it's no problem if we're doing a whole lot of pollution. It's got to get worse before it gets better. So what we can expect, based on this model, is that, yeah, the world's going through a time now of heavy carbon pollution, but in times to come it's going to decline because everybody gets wealthier, families will be smaller, lower demand, more attention to the environment. So making this kind of argument. And there's a lot of aid agencies in the wealthy world that have bought into this philosophy. So the idea that once everybody is rich, population growth will be low, and there'll be a good life for everybody. Now, the problem I have with some of these theories is that they don't really take a good view of ecosystems. They seem to assume that, like, the ocean is just inexhaustible and can keep providing all the resources people need forever after. So we proposed an alternative, more environmentally focused view based on thinking about how do people use ecosystems and what do they value about ecosystems. And if we think about this shift over time, so we start over here. This is ecological degradation, the amount of ecological degradation. So it's a bit like that one axis on the Kuznets curve. And the other one is wealth. So we start over here with, let's say, a relatively traditional society where people are simply living in smaller communities where they can get everything they need directly from the environment, right? That's a kind of accepted starting point for many trajectories of change in human society. And then what might happen over time is one of two different things. Either people start getting wealthier, they urbanize, they develop systems of distribution and consumption, they develop specialized labor, the economy shifts into a whole lot of other kinds of dynamic that maintain it in what we think of as a red loop. Or alternatively, that as the population grows, people might end up trying to make a living off smaller and smaller patches of land. So you see this in countries like Niger, for example, where it's traditional that the parents give their children a tract of land to farm. So if the population growth is too fast, you end up with more and more people farming smaller and smaller patches of land in increasingly less favorable farming conditions, because obviously you're not necessarily going to give your kid the best plot of land you've got. Right? And this can lead to what we think of as a green trap, where people struggle because there's inadequate food production and it's hard to get any kind of wealth together, basically. What's interesting is both of these can lead to collapse. So this one is the one you would think of leading to collapse and famine. You know, the kind of images you might have seen on TV about famine in Ethiopia or other parts of Africa. But this loop can also lead to collapse. So Sweden is a good example of this kind of dynamic. As Sweden's got wealthier and wealthier, the proportional contribution of agriculture to its economy has gone way, way down. So most of the Swedish economy now, there's still a fair-sized mining chunk, but a lot of it revolves around services. You know, big businesses like IKEA, for example, producing furniture. But what's driving that is production from other places in the world. So although the environmental quality in Sweden has improved hugely over the last 100 years, their impacts on forests around the world have been much higher. So this model is not intrinsically sustainable on its own because it actually leads to higher patterns of consumption. The only reason it works in our current time is because not everywhere has the same quality of life. If everybody were wealthy, this is going to lead you to here a red trap where you're over-consuming, and it's very hard to stop people doing that once they've experienced a good life, and ultimately leading to the same endpoint of collapse and famine. All right, so this is a hypothetical model. What do the data say if we look at actual numbers? So what I'm going to show you is a series of plots. Each of these dots here, black dots here, represents an individual country. And this is based on World Bank data, so there's no bias within the data set. The first thing you notice if you look at these data is this figure on the left. You'd expect this to be a bell curve, a normally distributed curve, showing basically that most countries are medium wealthy and some are really rich and some are really poor. But actually it's bimodal. There's two different peaks here. You've got a rich peak on the right here and a poor peak on the left in financial terms. This axis down here I'm going to show you a number of times. This is Human Development Index, or HDI. So it ranges from 0, which is a really basically undeveloped situation, to a value of 1. And that's based on a bunch of measures around the national economy, such as child mortality, people's access to school. It's not just purely financial. It's based on indicators that people are trying to use to actually estimate quality of life. Right, so if we look at how do different countries play out on some of these metrics, this is per capita GDP. So in the wealthy countries, that green curve, population growth rate goes up, per capita growth goes up. So they're basically converting people, more people makes more money. Whereas on the left-hand side here, population growth rate goes up, per capita GDP goes down. So if you live in this part of the world, then the more people there are, the less wealth you create rather than the more. Now if we look at how does this relate to ecosystems, so proportional reliance on natural resources. These are per capita GDP again, here on the X. And these are the rents. This is how much money you get back from natural resources of different kinds. That's agriculture on the left and forest resources on the right. And you can see that the lowest income countries are heavily dependent on agriculture all the way up here, whereas the wealthy ones, it's a relatively small proportion of their economy, even though the total volume might still be quite large. And the same with forest resources. So it's the poorest countries that depend the most on forest resources as a proportion of their total GDP. So population growth declines and per capita GDP levels off with increased levels of human development. The fonts have gone a little bit funny on this one. But basically this declining curve shows what happens to should have brought my glasses here, to population growth rate, right? So that's population growth rate on the axis here. As countries get wealthier, population growth does go down, but not down quite as far as you might think. And then as the wealth of the country increases, that development index does increase with wealth, but then it levels off. So beyond a certain point, being in a wealthier country doesn't give your citizens a better quality of life. And the other key thing that these data show, this is ecological footprint measured in a whole set of ways that, again, I'm not going to go into detail with. And this is Human Development Index here. The ecological footprint of the wealthy countries is much higher than that of the less financially wealthy countries. So you might be living in a place like Luxembourg, and it all seems sort of calm and serene and beautiful nature, but actually the impact of Luxembourg on the world is disproportionately massive compared to a country down here, for example, which might not look anything like so scenic, but is consuming far fewer of the world's resources per capita. So overall, wealthier countries consume more natural resources, both per capita and overall. All right, so if you don't like equations, you're welcome to look at this larval anglerfish on the right, which is a really cool thing. But we pulled this together with some simple equations, and by substituting out, we get this model down here, which is just a mathematical description that combines the different dynamics that I've spoken about now. And what does it show? It shows that neither Rostow nor Kuznets is really supported. What we've got is actually two groups of countries, and there's a bit of internal resilience in both of these groups. So resilience is not always good. The lower income countries here are trying to get into this ball, but there's barriers. There are real barriers there that prevent them from getting across that. Some of the countries that have managed this have done so through things like mineral extraction. So Chile, for example, has shifted from there over. This is a bit polarized because I've just taken the lowest quartile and the highest quartile of countries for this analysis. So there are a few in the middle here. By copper production, Chile has been able to generate enough wealth to get into this ball and then shift its reliance from natural resources. But it's not necessarily a solution because it still means that they're going to be consuming more than they were before. Right, so what are the implications of all of this for the ocean? The last bit of the talk now, I'd just like to focus a bit more on the ocean. There's many nations with diverse marine ecosystems, and they're developing nations in terms of development speak economically. So that development, the economic growth, is going to increase pressure on the sea. And getting richer is only going to shift those pressures from local to global. It doesn't solve the problem when they get richer. So is there a solution? And I think the only solution that I've been able to see is we need a different model for development and growth. We've got to shift to more equitable, just, sustainable solutions that are built on different values, to lower consumption, to focus on renewable energy, and to prioritize the environment over wealth. Otherwise, I simply don't see how so many countries on Earth can live basically a Western lifestyle without leading to some very severe consequences for the Earth. I'd like to focus in a bit on Australian coral reefs, because I think this might be a topic of interest to many people here. And one of the things that I've been wondering about is, are coral reefs a canary in the coal mine, or are they more like Monty Python's parrot? So are they dead, deceased, no more, demise, passed on, or are they actually just an early warning sign that still has some hope of recovery if we were to take them out of a dangerous environment? So the latest report from the Great Barrier Reef Marine Park Authority was released in style at Friday the 23rd of August at 4:30 p.m., which I cynically might consider an attempt to avoid the news cycles. And there's a detailed report which is actually extremely good. It lays out a really good, solid foundation of science. But what got me was the talking points they highlighted for the press from the report. So the current condition of coral reef habitats for the period ending December 2023 across the Great Barrier Reef has improved. The property's outstanding universal value as a World Heritage Area remains intact. And relatively few intense disturbances occurred over the period. So they completely ignored the massive 2024 bleaching event because this particular report had to terminate at the end of 2023. And so we might be wondering, is this the equivalent of the parrot seller stating that the dead parrot was simply pining for the fjords? So are we pining for the fjords here, or is this actually a reasonable reflection of what's going on? If we look at maps of what's happened on the Great Barrier Reef with coral bleaching, hopefully you can see the dates here. So these are several different bleaching events. The green here indicates reefs that did not bleach, and the red indicates areas of high bleaching density. And this is the most recent map. This is the 2024 aerial survey. What you can see here is that the reefs in the north got away reasonably intact, but all down the rest of the reef, including some areas that hadn't bleached before, there was extensive and really damaging bleaching. So one of my field sites is Heron Island, which is down here in the Capricorn Bunker, and I've been horrified by the photos I've seen, because that's been a fantastic reef for snorkeling and diving. So it's been massive changes from the perspective of someone who's been out in the field. And I've also seen places like Lizard Island just go from this very rich, vibrant community of corals to a much more simplified situation. So are coral reefs collapsing? There have been severe declines in areas of coral. Some or many species, I think, are going to be lost. There's a set of species that are not very resilient to marine heat waves, and it's quite likely that those will be lost. Will there be coral reefs in 2050? Well, probably. It's likely that there will be, but they're going to be different. They might be simplified. There might be some adaptation, and that's, I think, our main hope. There's still something like 50 billion live corals out there in the wild that are alive, and there's going to be very high selective pressure on those to adapt and respond to changes in the marine environment. So there's a chance that within those coral populations that there's the genetic diversity available to adapt in the kinds of ways that we hope they might. But we don't know for sure. I think the most likely cause is simplification. But it's also clear that there are some species that are quite resistant to marine heat waves, that don't bleach so easily, and that are likely to persist into the future. So a lot depends on adaptation by corals and also on our ability to reduce fossil fuel emissions. I think in the current climate, it's possible that we might see reasonable amounts of adaptation and persistence of reefs. If the Earth gets a lot hotter, I think that likelihood gets lower and lower with increasing heat. And we've got some panelists who'll be able to speak to this more knowledgeably than I can. So what can we do about this? How can we respond? So with one of my students, we've done some work looking at what are people doing in response to coral bleaching particularly. So there's a set of government policies that dictate how people should manage ecosystems. And these affect what we think of as adaptive capacity, the ability of human societies to adapt and respond to these changes. Climate change is obviously becoming a major driver that's impacting that adaptive capacity. The capacity here is useless to have capacity if you don't do anything with it. So that has to translate into adaptations. So things that people are doing to try and adapt to the ongoing crisis are things like diversification between livelihoods, within livelihoods, changes in the mode of operations, changes in natural resource management. And those lead to particular outcomes for human societies and for businesses, for example. So reef tourism is an example of an industry that's had to respond to coral degradation quite heavily. I'm afraid this bottom map's not displaying properly, but on these, we looked at operators who'd been affected by bleaching, which is the blue lines, and operators who had not, which is the orange line. So we basically got a treatment and a control. And classified based on interviews with all the people at all the locations indicated by the red dots here. It's a total of around 300 different operators. Grouped their responses into things that might be transformative, things that might be adaptive, or things that might simply be coping. What was interesting here, so it's 231 operators. What's interesting here is that the main response was spatial diversification. So people started using other locations that were less badly bleached, which is not necessarily a long-term successful response by tourism operators. There was a whole group that engaged in restoration as the second response. And again, I'm not sure that's likely to solve the problem, given that they're restoring corals that are equally vulnerable to marine heat waves as the previous ones. And the third option taken by people was product diversification. So for example, branching out from focusing on reefs to also including things you could do from the beach or things in open water using similar infrastructure. So to pull this together, we can think of the coral reef crisis. I'll take a moment to explain this figure. If you think of the area disturbed when there's a disturbance, so this would be the proportion of area disturbed. When you have a perturbation like a marine heat wave, it might impact only a small proportion of the area, or it might impact most of the area. And then on this other axis is a time axis, but it's adjusted for the speed of recovery. So if something recovers really slowly relative to the disturbance frequency, it would fall down here, whereas if it takes a long time to recover, it'll be up here. And what we've seen is coral reefs have experienced a whole set of impacts throughout their existence: cyclones, storms, impacts from marine mammals, for example, other things passing through reefs. But they've been able to sit up here because the proportion of area disturbed is relatively small, and the recovery time is relatively quick in relation to those particular disturbances. Now, what's worrying is that we've started to see things moving down here. So they're still relatively stable, but we've got high variance. So the proportion of area disturbed is increasing. The speed of recovery hasn't really changed a lot, but they're starting to move down into a situation where there's a lot of variance in coral cover or coral recovery rates. And the worry is that if marine heat waves become even more extensive and the frequency goes up, we're going to move into this situation where there's an unstable system and the possibility for collapse. But I think a lot depends still on the future of emissions and exactly how warm the oceans get. So this can be briefly summarized in this way. This just shows you shifts in the global economy. And then what's happened to coral cover. The Caribbean had a major crisis and has lost a lot of its reef. And on the Great Barrier Reef, coral cover has been declining. This is classically, if you look at this as distance and time, the responses used to be in the screen area here, and the nature of disturbances would be relatively small distances and relatively short time periods. What's happening now is that this is extended out. So the scale and frequency of disturbances has gone way up. There's new threats, and the new response has actually been to go down to the micro level and start thinking about how to genetically engineer heat-resistant corals. And so, to me, there's a blatant scale mismatch between what's happened on the ground or in the ocean and what people are doing in response. All right, so in closing, as the world changes, we urgently need theory that explains and predicts collapse and how to avoid it. There's lots of different ways that collapse can happen. Most of them are multi-causal. I think there's at least 14 different non-exclusive mechanisms. I don't think we should expect any single solution. There's no panacea. No one approach is going to solve everything in terms of avoiding or predicting collapse. But what I think we will see is a series of small-scale collapses in marine ecosystems, and that's much more likely than a big systemic collapse. But what's going to be critical is the timing and the extent at which those perturbations happen.